Welcome, everyone, to TechDaily.ai. The world of data and technology, well, it's constantly reshaping, isn't it? And how organizations manage their most valuable asset information has never been more critical. This deep dive is sponsored by Stonefly. They're your trusted solution provider and advisor in enterprise storage, backup disaster recovery, and advanced cloud infrastructure solutions. That includes hyperconverged systems, AI servers, and comprehensive security appliances. You can learn more over at stonefly.com. Okay, so let's unpack this. Today, we're diving deep into the fascinating and frankly often complex world of cloud databases. Our mission here is really to give you a shortcut to being well informed. We'll explore the fundamental differences between SQL and NoSQL, understand the critical trends shaping the next few years, and uncover practical, actionable strategies for cost optimization and effective data management in the cloud.
Yeah, and what's truly fascinating here, and I think you'll see this as a theme, is how cloud has fundamentally shifted. It's really transformed from just being, a technical choice into a genuine strategic asset for businesses. We're going to explore why this shift is absolutely crucial for any organization aiming for, well, digital agility and maintaining that competitive edge today.
I couldn't agree more. So let's start right there at that foundational fork in the road, SQL versus NoSQL. For someone just navigating this, what's the real core difference in their philosophy? What sets them apart?
That's the perfect place to start. So think of traditional relational databases, SQL databases, like a meticulously organized library, a very strict, predefined cataloging system. Data gets structured into tables with columns and rows, almost like a really well-designed spreadsheet, their core strength. It's handling complex queries and transactions that demand absolute data integrity. We often talk about ACID properties here: atomicity, consistency, isolation, durability. This ensures every transaction is solid, reliable, complete. Common examples you'll run into are things like MySQL, PostgreSQL, Oracle.
Okay, the organized library. And then in a pretty stark contrast, you have the more flexible, non-relational or NoSQL databases. How do they approach data differently?
Right, so NoSQL breaks away from that rigid structure entirely. They offer flexible schemas, non-tabular models. We're talking document-oriented, key-value stores, graph databases, wide column stores. Lots of variety. Their real power comes out when you're dealing with a huge mix of data types: structured, semi-structured, maybe even completely unstructured data. This makes them incredibly adaptable for modern apps. Think things like MongoDB, Cassandra, DynamoDB, or Amazon Document DB. Now, this difference in how they model data, it directly impacts a really crucial trade-off, especially in distributed systems. It's often simplified by the CFP theorem: consistency, availability, and partition tolerance. So SQL databases, they generally prioritize strong consistency. That means ensuring every read operation gets the absolute latest written data. Super important for things like, say, financial transactions. But this focus on consistency can sometimes come at the expense of availability. Maybe if the system needs to pause briefly to make sure everything's perfectly synchronized.
Okay, so SQL prioritizes that strong consistency. What's the trade-off then for NoSQL with all its flexibility? Exactly. So NoSQL databases, they typically prioritize basic availability and partition tolerance. They often opt for something called eventual consistency. What that means is data will eventually become consistent across all the different nodes in the system, but maybe not instantly. It's often associated with base guarantees. That's basic availability, soft state, eventual consistency. Understanding this distinction, this trade-off, is absolutely crucial when you're designing your application. It's really about balancing that need for, say, real-time responsiveness versus absolute data integrity. Which one you lean towards depends entirely on your specific workload and, well, your business priorities.
That clarity on the core difference and those trade-offs is really invaluable. Okay, now let's zoom out a bit to the broader landscape. You mentioned cloud is no longer just an IT utility. It's rapidly becoming a central business enabler. Our sources definitely highlight that organizations are demanding more flexibility, scalability, and efficiency in how they manage and access data. That really cements cloud's role as a strategic asset. And speaking of strategic assets, Gartner recently highlighted six pretty pivotal trends that are set to define cloud strategies right through 2029. First up, and maybe a bit surprising, cloud dissatisfaction is rising. By 2028, maybe a quarter of organizations could report significant dissatisfaction. What the analysis points to is that the fix isn't just a clear strategy, but getting more specific. Integrating a FinOps framework right from day one to proactively manage costs, and doing rigorous architectural reviews to make sure realistic expectations are set. Without that discipline, runaway costs and unmet expectations are, well, almost inevitable.
That's a really critical point about setting expectations and managing costs up front. Okay, what else is coming down the pike?
Second, AI and ML demand will absolutely skyrocket. By 2029, a staggering 50% of cloud compute usage will likely be driven by AML workloads. That's a massive leap from current levels, which are under 10%. The hyperscalers, AWS, Azure, Google Cloud, they're already building platforms combining real and synthetic data, distributing intelligence across hybrid environments. This shift means databases need to be optimized for entirely new types of data processing and at a massive scale. Third trend, persistent multi-cloud complexity. Over half of multi-cloud efforts, sadly, might fail to deliver the expected benefits by 2029. This is largely due to interoperability headaches and fragmented operations. Success here really requires clearly defined use cases. It's not just about being multi-clouds for the sake of it, and you need careful planning for how those federated workloads will actually function. It's not about using every cloud, but using the right clouds for specific jobs.
Right, so specialization becomes more important then.
Precisely, which leads to the fourth trend. We'll see the rise of industries-specific cloud platforms. By 2029, more than half of organizations will likely leverage tailored cloud solutions specifically for vertical sectors, think healthcare, manufacturing, finance. These platforms offer things like pre-built compliance features, specific workflows, and industry-relevant analytics to accelerate outcomes. It kind of sidesteps the need to build absolutely everything from scratch. Fifth, digital sovereignty takes center stage. By 2029, over 50% of global multinationals are expected to adopt digital sovereignty strategies. That's way up from fewer than 10% today. This is really being driven by concerns around data residency, privacy laws, and frankly, geopolitical shifts. It's pushing cloud providers to offer more localized control and specialized data governance solutions. And finally, a trend that really touches everyone. Sustainability isn't optional anymore. With AI's huge momentum, cloud energy consumption is surging, and that's leading to increased environmental scrutiny. Both the providers and us, the users, we have to diligently measure, manage, and reduce our carbon footprints. This is increasingly going to influence architectural choices, even down to database locations and configurations.
Wow, okay. So what does all this mean for you, our listener, trying to navigate this rapidly evolving space? These trends, they fundamentally underscore that cloud isn't optional anymore. It's truly the backbone of digital agility and gaining that competitive advantage. They highlight the increasingly complex demands being placed on cloud databases, pushing organizations like yours to constantly reevaluate your data architectures, your latency strategies, your governance models, all to support scalable intelligence and compliance across these complex, often multi-cloud environments. It's definitely a lot to consider. And with all that complexity, it's important to remember that cloud databases do offer some really compelling advantages. Let's touch on the pros first. Number one is scalability. It's theoretically limitless, right? Allowing you to dynamically adjust resources up or down to match demand. You really only pay for what you use, avoiding those costly over-provisioning mistakes. Then there's cost efficiency. Cloud pretty much eliminates the huge capital expenditure, the CapEx, for buying and setting up on-site servers. And it reduces ongoing operational expenses, OpEx, by outsourcing maintenance and upgrades to the provider.
Exactly. And a huge benefit that sometimes gets overlooked is disaster recovery. Cloud databases typically offer things like automatic backup generation, hosting those backups on external devices, often in multiple locations, even different availability zones for high availability and geographical fault tolerance. This systematically reduces system failure risks. Achieving that kind of resilience on premises is incredibly difficult and expensive.
That's a very good point. And finally, accessibility. Your data is accessible over the internet from anywhere, anytime. That promotes better collaboration, especially across regions, and it simplifies application development because teams can spin up and tear down databases for testing as needed without the usual IT bottlenecks.
Yeah, those benefits are powerful, absolutely. But it's crucial, really crucial, to understand the cons as well. Overlooking them can lead to some significant headaches down the road. One major concern is vendor lock-in. Relying heavily on proprietary solutions from just one cloud provider can make switching clouds later really difficult or very costly. For example, migrating from a managed relational database service in, say, AWS to Azure isn't natively supported. It can lead to significant expense and major operational disruptions if you try a full infrastructure migration. You really need to think about your current and future cloud needs right from the start.
That makes a lot of sense. What about reliability? Cloud is often sold on reliability, but you mentioned risks.
Well, yes, there are still downtime risks. Despite all the advanced high availability measures, cloud outages can happen, and they do happen. Network failures, misconfigurations, unexpected traffic surges. That 2021 AWS outage, It wasn't just some small technical glitch. It sent ripples through entire industries. It disrupted major services and really proved how deeply ingrained cloud services have become in everything we do. It's a powerful reminder that even with all the built-in resilience, no system is entirely immune. So regular backups and actually testing your disaster recovery strategies are absolutely crucial to mitigate this risk. Vulnerability is another factor to keep front of mind. While the major cloud providers do a great job securing the underlying infrastructure, the hardware, the network, you are still responsible for securing your own database on top of that infrastructure. A key insight many overlook is the subtle danger of misconfigurations, especially in these fast-moving serverless environments. Automated policy enforcement and continuous auditing, they're basically non-negotiable now to avoid costly data exposures. And with multi-tenancy, where multiple users might share a single database instance, there's always that possibility of one tenant potentially accessing another's data if your access controls aren't absolutely watertight. Strong authentication, data encryption, these are vital. And finally, related to that is compliance. Failing to protect user data can lead to severe reputational damage, massive fines, even lawsuits. Look at the Equifax breach back in 2017, sensitive personal info exposed, and they ended up paying over $500 million in a settlement. Understanding the shared responsibility model with your vendor and conducting routine audits are essential to avoid these kinds of costly compliance nightmares. It's a partnership, but you own a significant piece of that security responsibility.
Okay, so given these critical considerations, unlocking efficiency through database cost optimization becomes absolutely paramount. Now, regardless of whether you're using SQL or NoSQL, there seem to be some universal principles. Things like proactive monitoring and setting up alerts using cloud tools like CloudWatch are essential, right? Tracking CPU, storage, network, estimated charges. And the fundamental principle, it seems, is always selecting the right instance types and storage options that genuinely align with your workload demands, but without sacrificing necessary performance. Okay, expert, let's dive into some specifics, maybe starting with SQL optimization.
Absolutely. For SQL database optimization, really key first step is identifying underutilized resources. You need to pinpoint things like idle instances or read replicas that just aren't earning their keep. Setting thresholds and automated alerts helps catch these. Then, critically important, is right-sizing instances. This means selecting instance types that offer the optimal balance of compute power and memory specifically for your application's workload. Over-provisioning just wastes money, but under-provisioning causes performance bottlenecks. And always perform a thorough performance impact analysis before you downgrade an instance, especially if it's in production.
That makes sense. Don't just cut costs blindly. What about the storage itself for SQL?
Right. Optimizing storage. You typically have choices. General-purpose SSDs like GP2 or GP3 on AWS often offer a great balance of cost and performance, good for dev test or moderate I/O. Or, for those really performance-critical I/O-bound workloads, you might need to opt for provision IOPS SSDs like IO1 or IO2, which guarantee consistent and predictable I/O throughput, though they cost more. Another powerful technique, especially for predictable long-term workloads, is utilizing reserved instances, often called IIs. By committing to use a specific instance type for 1 or even 3 years, you can get significant discounts compared to on-demand pricing. And a few more things specifically for SQL. Optimize those inefficient SQL queries. Use techniques like query rewriting or adding appropriate indexes to speed things up. But be smart about indexing. Balance the need for faster retrieval against adding too much storage overhead. And finally, establish smart backup policies. Think about using tiered storage for older backups and compression to reduce your overall storage footprint over time.
Those are some really clear, actionable strategies for SQL. Now, shifting gears to NoSQL database optimization, what tailored techniques can yield significant savings there?
Well, many principles overlap, actually. Just like with SQL, instance type selection is critical. You need to choose instances based on whether your workload is primarily read-heavy, needing more memory, or write-intensive, requiring high I/O capacity. And for workloads that fluctuate a lot, autoscaling is a really powerful tool in the NoSQL world, too. It automatically adjusts the number of instances based on real-time demand. This lets you avoid paying for over-provisioning during peak loads and automatically scales things down during quiet periods.
That makes sense for dynamic loads. And for managing the sheer volume of data that NoSQL often handles, how can you optimize costs there?
Great question. For managing the data lifecycle and the associated costs, techniques like data archiving and time to live, TTL, are invaluable with NoSQL. You can move older, less frequently accessed data to cheaper storage tiers automatically. And TTL lets you set rules for automatic deletion of data that has a defined lifespan, like session data or temporary logs. Also, integrating a database caching layer, something like Amazon Elasticache, can really help. It serves frequently accessed data much faster directly from the cache, which reduces the read operations hitting your primary database and consequently lowers your I/O costs.
Interesting. So even with NoSQL's flexible schema, query optimization is still important.
Oh, absolutely. Even with the flexibility of NoSQL, query and index optimization remain crucial for both performance and cost control. Bad queries cost money, no matter the database type. And for non-production databases, dev, test, staging a simple but super effective technique is scheduling start-stop. Automate shutdowns during off hours or weekends. You only pay for compute resources when they're actively being used. Also consider data compression. Using efficient algorithms like Snappy or gzip can significantly reduce storage space and network bandwidth consumption, especially for document-style NoSQL databases. And you can often reduce overhead and improve efficiency through connection pooling and bulk operations, reusing database connections and grouping multiple write operations together. Finally, watch those data transfer costs. Keep your database cluster and the applications that use it within the same cloud region if possible. Explore options like private network connections to minimize network transit costs, which can add up. And similar to RIs for SQL, if you have predictable NoSQL usage, consider purchasing savings plans for compute to reduce your overall costs.
Stepping back from specific optimization tactics, understanding the underlying schema design philosophies is also key to efficiency. And it really highlights that core difference between SQL and NoSQL again. SQL databases generally follow what's called a normalized design. The goal is to minimize data duplication, keep things tidy, and have relationships between data strictly enforced by the database itself.
Right, so it's all about avoiding redundancy and letting the database manage those strict relationships.
Precisely. NoSQL, on the other hand, often embraces denormalized data models. This means you might deliberately add redundant copies of data, often to improve performance, especially for read-heavy workloads. In this model, the relationships between different pieces of data are typically managed more by the application logic itself, rather than being strictly enforced by the database constraints. It gives the application potentially more control and flexibility, but it also shifts some of that data integrity responsibility onto the application code.
Okay, that makes sense. Now, building on all these optimization techniques and design philosophies, a really revolutionary shift we're seeing in cloud environments is the rise of serverless databases. What are the core advantages there? And maybe more importantly, when might they not be the right fit?
That's a fantastic question, because serverless really does change the game for many types of applications. The benefits are pretty compelling. You get automatic scaling both up and down to perfectly match demand. There's a true pay-as-you-go cost model, where you literally only pay for the exact compute and storage you consume, often down to the millisecond or the request. This usually leads to significantly improved developer productivity because teams can focus purely on application logic instead of managing servers, patching OSs, all that stuff. Plus, they typically come with high availability and durability built right in, often with data automatically replicated across multiple data centers. And they usually have robust security features integrated. Think things like Azure Cosmos DB, Google Cloud Firestore, or Amazon DynamoDB.
Those benefits sound almost too good to be true sometimes. So where's the catch? When would you advise someone against going serverless for their database?
Yeah, it's true. They're not a silver bullet for every single use case. You might not want to use serverless for, say, highly consistent, predictable workloads. In those cases, a traditional fixed-cost, server-based approach could paradoxically end up being more cost-effective because the usage is so steady. Serverless can also sometimes experience what are called cold starts. That's where an inactive function takes a brief moment longer to initialize when it's first called. This might negatively affect applications that are extremely sensitive to latency variations. Serverless databases may also struggle with really complex transactions that require strict traditional ACID properties across multiple records or tables, or they might just not be the best fit for very large-scale batch processing jobs or situations where you need very specific granular control over the underlying hardware configuration. It really is, like always, about matching the right tool to the specific job at hand.
Okay, we've really covered a lot of ground here. We've taken a deep dive into those fundamental differences between SQL and NoSQL databases. We've explored the, well, exciting but also challenging trends shaping cloud strategies for 2025 and beyond, and we've outlined some powerful, actionable optimization techniques. I think the core message is clear. Choosing the right database architecture for your needs and implementing continuous ongoing optimization are absolutely paramount for maximizing the value you get from the cloud and keeping those costs under control.
Absolutely. And if we try to connect all this to the bigger picture, the future of data management, it isn't just about picking one database over another. It's really about strategically designing an adaptable, cost-efficient, and resilient data architecture, one that can anticipate and handle the ever-increasing demands of things like AI, evolving global regulations, and just shifting business needs. So the question to maybe leave you with is, how will you leverage these insights? How will you transform your organization's data challenges into real long-term competitive advantages? This deep dive hopefully leaves you with plenty to mull over.